Hi, welcome to How to Interpret a Scientific Measurement with Gaussian Error Bars. In this video, we'll be looking at how to interpret a measurement that is quoted with Gaussian error bars. We'll look at a hypothetical particle physics measurement, the measurement of the mass of a newly discovered particle. We'll see what this measurement, along with its uncertainty, tells us about the true value of the particle's mass. We'll also see what implications the measurement could have for hypotheses which make predictions about the value of the particle's mass. We'll mostly leave mathematical details out of this video. Instead, we'll point to other videos where more rigor can be found. So here, we'll just look at a toy scenario. We'll pretend that an experiment has reported its result with an error bar, and we'll see what this implies about the parameter being measured. If you'd like an example with more scientific detail, you can check out Unexplained Mysteries of the Standard Model, Grand Unified Theories, and Limits on Proton Decay, available on this channel. In that video, we look at a real result on proton decay from the Super Kamiokande experiment in Japan. We give some background information on why we might want to experimentally look for proton decay, discuss how it's searched for, and discuss how they get their results. Okay, let's get started. Let's imagine that a particle physics experiment has discovered a new particle. They've measured its mass m and done extensive studies to calculate their measurement uncertainty. They quote their result as 385 plus or minus 17 GeV over c squared. They take their errors as Gaussian distributed, and the quoted number for the uncertainty is the standard deviation sigma of the error. Our goal here is to see what this measured value of m measured, tells us about the true value of m true. Let's start by explicitly stating what this result, along with its error bar, means. When we say that the result of the measurement is m measured equals 385 plus or minus 17 GeV over c squared, what we mean is this. We measure the mass and obtain 385 GeV over c squared. If the mass was measured via the same methods many times, and the measurements were completely independent, we expect that m measured would be Gaussian distributed around m true with a standard deviation of 17 GeV over c squared. To think about this, let's step back and pretend that we don't yet know their measured result. Instead, we just know that they take their measurement errors as Gaussian distributed with a standard deviation of 17 GeV over c squared. For example, let's briefly imagine that m true is 392 GeV over c squared. Because of measurement uncertainties, when they do their experiment, they won't obtain m measured exactly equal to 392 GeV over c squared. Instead, m measured is equal to m true plus the measurement error. If their measurement error is Gaussian distributed with a standard deviation of sigma equals 17 GeV over c squared, then m measured will be Gaussian distributed around m true, that's 392 GeV over c squared, with a standard deviation of sigma equals 17 GeV over c squared. Now, let's borrow some results from the video Features of the Gaussian or Normal Distribution, Part 2, Probability Bands and the 68-95-99.7 rule. In that video, we see that if a quantity is Gaussian distributed, about 68% of the time, its value falls within 1 sigma of the mean mu. It is similarly within 2 sigma approximately 95% of the time, and within 3 sigma about 99.7% of the time. These results compose the 68-95-99.7 rule. So, if m true is equal to 392 GeV over c squared, the probability of m measured falling within sigma, that's 17 GeV over c squared, of the mean, which is 392 GeV over c squared. That means that it falls within the range 375 to 409 GeV over c squared, is about 68%. Here we show that range in blue. The probability of m measured falling within 2 sigma, so that's within 34 GeV over c squared, of m true. So that means between 358 and 426 GeV over c squared, is about 95%. And the probability of m measured falling within 3 sigma of 392 GeV over c squared, so between 341 and 443 GeV over c squared, is about 99.7%. Also, it's important to realize that it is possible for m measured to fall many sigma away from m true. However, while it is possible for the measured value to fall very far away from the true value, it is rather unlikely. Okay, so we've seen the probability for m measured to fall in certain ranges around m true, given m true. But we don't know m true. We know m measured to be 385 plus or minus 17 GeV over c squared. So what can we say knowing its measured value? First, let's see what we can say about the compatibility of the measured value with the predictions of some hypotheses. Let's say we have 2 hypotheses, which we'll just call hypothesis 1 and hypothesis 2. Perhaps these hypotheses were proposed to explain other observations at other experiments. But let's say that hypothesis 1 predicts that m true equals 368 GeV over c squared. And at the same time, hypothesis 2 predicts that m true equals 419 GeV over c squared. What can we say about the compatibility of the measured value of m measured, with either of these hypotheses? Before continuing, we should briefly make 2 points. First, realistically, the predictions of hypotheses 1 and 2 would have uncertainties associated with them. We'll assume that these uncertainties are small enough that we don't have to take them into account. Second, it would be non-trivial to establish that a newly discovered particle is the particle that either hypothesis 1 or hypothesis 2 predicts to have a mass of m true equals 368 GeV over c squared or 419 GeV over c squared, respectively. When the particle now thought to be the Higgs boson of the Standard Model was discovered in 2012, physicists did not know that that's what it was. Since then, many measurements have been made to see if the particle's traits are those of the Higgs boson predicted in the Standard Model. So far, the particle discovered in 2012 at the Large Hadron Collider is consistent with being the Standard Model Higgs boson. So these are definitely non-trivial issues in reality, but we're going to ignore them in our simplified scenario here. Okay, let's get back to looking at what we can say about the compatibility of m measured equals 385 plus or minus 17 GeV over c squared with hypotheses 1 and 2. Okay, so if hypothesis 1 is correct, m true is equal to 368 GeV over c squared. So we would expect m measured to be Gaussian distributed around m true, that's 368 GeV over c squared, with a standard deviation of sigma equal 17 GeV over c squared. But if hypothesis 2 is correct, m true is equal to 419 GeV over c squared. Then m measured would be Gaussian distributed around m true equals 419 GeV over c squared, with a standard deviation of sigma equal 17 GeV over c squared. Now let's compare these to the measured value of the mass. So m measured equals 385 plus or minus 17 GeV over c squared. M measured is one standard deviation, sigma equal 17 GeV over c squared, away from the prediction of hypothesis 1, which was 368 GeV over c squared. M measured is two standard deviations away from the prediction of hypothesis 2, so that was 419 GeV over c squared. Let's again use the 68, 95, 99.7 rule and compare m measured to the hypotheses predictions. Let's first imagine a scenario where hypothesis 1 is correct and m true is equal to 368 GeV over c squared. M measured is 1 sigma away from the prediction of hypothesis 1, shown here on the edge of the blue range between m true minus 1 sigma and m true plus 1 sigma. Before the experiment takes place, we would say that there was about a 68% chance that m measured would fall within the blue band. And there was about a 32% chance that m measured would fall outside the blue band. Both of these probabilities are not small, so obtaining a value of 385 GeV over c squared for m measured would not be weird at all. Now let's look at the scenario where hypothesis 2 is correct and m true is equal to 419 GeV over c squared. M measured is 2 sigma away from the value of m true predicted by hypothesis 2, 419 GeV over c squared. Again, using the 68, 95, 99.7 rule, the probability for m measured to fall in the 2 sigma band, shown in red, is about 95%. So the probability that m measured would fall more than 2 sigma away from m true is only about 5%. So if hypothesis 2 is correct, getting a value of m measured as far away from m true as 385 GeV over c squared is uncommon, but not rare. So we would probably say that hypothesis 1 is completely compatible with the measured value of the mass, m measured equals 385 plus or minus 17 GeV over c squared. On the other hand, there is some tension between the prediction of hypothesis 2 and observation, but it is probably not strong enough for us to give up on hypothesis 2 just yet. What happens if the experimenters improve their experiment? let's say that the experimenters try to improve their result. They may take more data or change their analysis to reduce their uncertainties. Then they measure m again. This time they report m measured equals 380 plus or minus 8 GeV over c squared. And again, the errors are taken to be Gaussian distributed. Now, hypothesis 1 still predicts that m true equals 368 GeV over c squared, and hypothesis 2 still predicts that m true equals 419 GeV over c squared. But now the experimental uncertainties have been decreased. Each hypothesis predicts that m measured will be Gaussian distributed around m true with sigma equal to 8 GeV over c squared. Now let's compare these predictions with the new value of m measured. Now, the uncertainty wasn't the only thing that changed between the old measurement and the new. The quoted value of m measured also changed to 380 GeV over c squared, shown by the arrow on the plot. Let's compare this to the prediction of hypothesis 1, m true equals 368 GeV over c squared. Here, the absolute value of m measured minus m true is equal to 12 GeV over c squared. Now sigma equals 8 GeV over c squared, so m measured is 1.5 sigma away from m true, and that's quite compatible. Now let's look at the prediction of hypothesis 2, m true equals 419 GeV over c squared. Now the absolute value of m measured minus m true is equal to 39 GeV over c squared. And again, sigma is equal to 8 GeV over c squared, so m measured and m true differ by 4.9 sigma. In a situation like this, unless a problem is subsequently found with the experimental result or its error bar, hypothesis 2 probably wouldn't be taken seriously anymore. So we can see that the compatibility between m measured and hypothetical values of m true can be quantified. Now let's think of some other questions that we might want answers to. First, let's clarify what we've done so far. Up until this point, we have been asking questions like, assuming that hypothesis 1, or hypothesis 2, is correct, is the measured value of the mass reasonable? Now, we have not asked questions like, given the measured value of the mass m measured and its error bar, what is the probability that hypothesis 1, or hypothesis 2, is correct? Or, given m measured and its uncertainty, what is the probability that m true lies in a certain range? Now, that first question is too complicated to address here, but let's think about that last question. So let's return to our original scenario, where the experiment reported m measured equals 385 plus or minus 17 GeV over c squared with Gaussian errors. We've seen above that if we know m true, we can make statements about the probability for m measured to fall in certain ranges. But can we do the reverse? Given m measured, what can we say about the probability that m true falls in some range? It turns out that given m measured, we can make statements about m true as long as we are willing to make some assumptions. We can do this using something called Bayes' Theorem. We won't go through the details or derivation of Bayes' theorem here, but for more information, you can look at the videos in the Bayesian playlist available on this channel. Now, Bayes' theorem is the possibly cryptic-looking relation that's read as the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. We can use Bayes' theorem to make statements about the probability distribution of M true given our knowledge of M measured. However, to do this, Bayes' theorem requires that we make some initial assumptions about the probability distribution of M true evaluated before the measurement takes place, or equivalently, pretending that the measurement hasn't taken place. So here, we'll make a particularly simple assumption. We'll assume that M true is between 0 and 1000 GeV over c squared. Also, let's say we don't have any reason to think that certain values of M true in this range are more likely than others. So we'll assume that all values within this range are equally likely. In other words, the probability for M true to be between 0 and 100 GeV over c squared is the same as the probability for it to be between 100 GeV over c squared and 200 GeV over c squared, and the same as the probability for it to be between 200 GeV over c squared and 300 GeV over c squared, etc. So that's the probability distribution we'll assume for M true before the measurement. Now we'll use Bayes' theorem to get the probability distribution of M true after the measurement. We won't go through the calculation here. However, a very similar calculation is done in detail in the 4-part series Why Bayes' Theorem is Important, available on this channel. So, given the above assumptions, along with the result that M measured equals 385 plus or minus 17 GeV over c squared, where the error is Gaussian distributed, Bayes' theorem gives the following. The probability distribution for M true is Gaussian distributed about M measured equals 385 GeV over c squared, with a standard deviation of sigma equals 17 GeV over c squared. So the probability distribution for M true, given that M measured is equal to 385 plus or minus 17 GeV over c squared with Gaussian errors, looks like this. The probabilities for M true to be within 1, 2, or 3 sigma of 385 GeV over c squared are given by the 68, 95, 99.7 rule. Now, it might seem not so surprising that for M measured equals 385 plus or minus 17 GeV over c squared with Gaussian errors, we conclude that M true is Gaussian distributed about 385 GeV over c squared with a standard deviation of sigma equals 17 GeV over c squared. But it is important to remember that this result required an initial assumption about the probability distribution for M true before the experiment takes place. Also, other starting assumptions are possible, and which one you choose will affect your result. On the bright side, though, any initial assumption with a probability distribution for M true that was constant within a few sigma of 385 GeV over c squared and reasonably behaved elsewhere would have given essentially the same result. And the effects of the initial assumptions can be mitigated by improving, that means reducing, the size of the uncertainty on the measurement. Now, before we finish up, we should make one final note. While quoting Gaussian uncertainties is common in the reporting of scientific results, this is not the only way to report uncertainties. so it is important to pay attention to how results are reported when perusing the scientific literature. Okay, let's summarize. Scientific measurements are often reported using Gaussian uncertainties. Here we've looked at the hypothetical measurement of the mass of a newly discovered particle and seen how to interpret the result and its uncertainty. In doing so, we've seen how we can compare hypotheses with measurements which have Gaussian error bars. We have also seen how we can use Bayes' theorem to make probabilistic statements about the true values of parameters, as long as we are comfortable with making some starting assumptions about those parameters. For more information, you may wish to view the videos referenced above. Links to these videos are also given in the video description below.